What things do you see in this image? Well, there's a circle, a hexagon, and a star. What you've just done is something called set prediction. The answer is a collection of objects, but the order that these objects are in doesn't matter. They can be in any order. This makes the collection of objects a set. Many things can be thought of as a set, like agents in an environment, the instruments in a piece of music, or atoms in a molecule. In general, thinking about problems in terms of sets is really useful whenever we have collections of individual things, but we don't care about the order of the things. The problem of set prediction is about this abstraction of, say, an image with lots and lots of pixels to a small set of discrete objects, which is much easier to reason about. Humans do this from a young age without even thinking about it, and we would love our machine learning models to be able to do the same. So, how do we get them to do set prediction? It turns out that while sets are really useful, the fact that they are orderless also makes them quite tricky to work with. In particular, in this video, I will tell you about a new kind of trickiness, which will lead us to the fresh new concept of something called multiset-equivariance. This lets us understand why self-attention, like used in a transformer, is not able to represent some functions that would be useful for set prediction, and we'll get to a concrete example of this later. After this, I will show you the only set predictor I know of that has this new property that we want, and how to improve it with implicit differentiation. But first things first, let's start with what exactly I mean by a set. When I say set, what I mean is an unordered collection of vectors. Each vector describes some information about an element in the set. For example, if we have a set of objects, the vectors could encode the position, color, and other properties for each object. We will always have a finite number of vectors in our set, and set prediction is simply the problem where the output that we want is such a set of vectors. So far, I've been talking about sets as you would expect them from maths. However, for computation, we have to store these orderless things in computer memory, and memory is very much ordered. The typical solution is to just store them as a list of vectors in some order. The order of the elements is irrelevant, so we can just pick any arbitrary order that we want. This allows us to use lists, which are much easier to work with, to represent sets. It's actually better to think of these lists as representing multisets rather than sets, so duplicates are allowed. Why is this the case? For example, AAB and AA plus epsilon B are almost the same in terms of the list representation. But in sets, duplicate elements are meaningless, so the sets they would represent are wildly different, they're not even the same size. This means that making a tiny change to the list representation by epsilon could lead to a big discontinuous change in the set, and we would like to avoid such discontinuities if possible. If we instead think of these lists as representing multisets, we just keep any duplicates, so there's no problem with discontinuities. This is actually quite important, so keep this in mind for later. You should think of existing set prediction models as operating on multisets, not sets. This may seem a bit pedantic for now, but we'll see later why this distinction is so important, even if we never actually encounter any exact duplicates. Now that we have a list representation of our multiset, we have to be careful to still treat these lists as if they were orderless. We picked an order completely arbitrarily, so we would like our model to not rely on this order. There are two properties in the literature that are helpful for this. Permutation invariance means that when changing the order of the input, the output vector must stay the same. For example, if you sum these elements together, you can sum them in any order you want without changing the result. Permutation equivariance, or as I prefer set-equivariance, means that when changing the order of the input, the output list should change order in the same way. You can think of each input element as being linked to an output element, and they always have to change order together. This property of set-equivariance is really the key behind how many of the recent set prediction models work, like slot detention and data, the transformers for object detection. You start with some initialization for a set on the left, and it gets updated with a bunch of set-equivariance steps, conditioned on an input, until you get the set that you want to predict on the right. For example, in data, Each of these set-equivariance steps is self-attention or an MLP that is shared across elements. And in the past, it was thought that set-equivariance is exactly what we want for the set predictors, but I'm here today to change that. One property of set-equivariance is that if you have an input with duplicates in it, then they must stay duplicates in the output. Let's say the second output is not C, but something different in E. And I'll just keep a copy of the output on the side for us to keep in mind. Set-equivariance means that when swapping the first two elements in the input, we must also swap the first two elements in the output. That's just what set-equivariance is. Now, the input representation is still exactly the same as before, we just swap two A's. Therefore, the output must also still be the same. So we have that ECD is equal to CED, so C and E must be the same. In other words, a set-equivariant function must map two equal elements in the input to two equal elements in the output. There's no way around that. Self-attention and slot attention are set-equivariant, and they have this exact limitation. For example, in self-attention, if you have two equal elements somewhere in the network, you will get two equal queries, which will give you two equal elements, which will give you two equal queries, and so on. Is this actually a problem though? Here's a function that could be useful when solving a more complex set prediction task, but it's impossible to model with set-equivariant functions. It takes a list of two scalars, representing a multiset, as input and pushes them apart. Whichever of the two inputs is the smaller value, we subtract one from it, and whichever is bigger, we add one to it. For example, in input 1, 2 gets pushed apart to be 0, 3. The smaller one gets turned into the 0, the bigger 2 gets turned into the 3. If you try a few values, you will see that it behaves just like a set-equivariant function. Changing the input order means changing the output order. However, what happens when you put in two equal values? Well, we can break the tie in the output order arbitrarily, so let's say 0, 0 gets pushed apart to be -1, 1. And now we're mapping two equal elements to two different elements, so it can't be set-equivariant. And indeed, changing the input order does not change the output order, which it would have to do for set-equivariance. This is a bit strange. Most of the time this function is set-equivariant, and when it's not equivariant, when the inputs are equal, we don't really care about the output order anyway. The output represents a multiset, so the order doesn't really matter. Either way to resolve the tie would be fine. So it seems that set-equivariance is too restrictive. There are these perfectly reasonable functions for multisets that are impossible to model with set-equivariance. How do we solve this? As a reminder, the key difference between multisets and sets is whether duplicate elements are allowed or not. So, we want a new property that is still related to the traditional set-equivariance, but it should do something different about these multiple equal elements. And that's exactly what this video is about. The new property Multiset-equivariance still means that changing the order of the input should change only the order of the output, but specifically for equal elements in the input, we no longer care about their output order at all. We can put outputs for equal elements in any order, they don't need to be linked together like before. This makes Multiset-equivariance a relaxation of set-equivariance. This is really what allows equal elements to be mapped to different elements, so we can turn an input with duplicates into an output without duplicates. The push-apart function is not set-equivariant, but it is multiset-equivariant. As an aside here, you might have noticed that this push-apart function seems to be discontinuous, because there's this if here. Usually, we don't like discontinuous things, since it often makes the model difficult or impossible to train, and we lose a lot of nice guarantees about its performance. But in this case, it's actually not a problem, because it's a very specific kind of discontinuity. The key here is that even though the list representation is indeed discontinuous, the multiset that it represents isn't. Basically, it only seems discontinuous because the elements are being swapped here. If we consider what these lists are representing, multisets, the order doesn't matter, so this discontinuity disappears. functions that are not set-equivariant but multiset-equivariant will tend to be like this, where even though the list representation looks discontinuous and troublesome, the underlying multiset is still nice and continuous, so learning isn't a problem. If there's one thing I want you to take away from this video, it's the summary of all the properties that I've been talking about. When a function is set-equivariant, it means that the inputs are exchangeable without affecting the results. But we have this limitation of not being able to separate equal elements. When a function is not equivariant at all, it means that we can separate equal elements in the input, but now we don't have the nice property that the elements are exchangeable without affecting the results, so we lose a lot of sample efficiency. There are n factorial number of list representations for the same multiset, so it's difficult for a model to learn to never rely on the order. Last but not least, when a function is not set-equivariant, but it is multiset-equivariant, then we really get the best of both worlds. The elements are exchangeable, which gives us good sample complexity, and we are also able to separate equal elements, so we are less restricted than with set-equivariance. I won't go into it here, but in the paper there's an experiment that confirms exactly these properties on sample efficiency and separating equals. And it's important that this inability to separate equal elements is a problem even when there aren't ever any exact duplicates. Because we're working with continuous models, the behavior for exactly equal elements will be similar to the behavior for similar elements. Impossibility to separate equal elements means difficulty when trying to separate similar elements. And there are lots of reasons why elements might be similar. We often use small random initializations for the multiset. Our model can have oversmoothing issues, like we often see in graph neural networks. Values could be zeroing out elements, or sigmoids and tangents could be saturated. Or similar elements could occur simply because they are part of the dataset that is being used. So, while multiset-equivariance specifies what happens for exactly equal elements, it's really more about how well we can do for similar elements, which are much more common. If we take a step back and look at the landscape of set predictors, we have quite a few that are set-equivariant, we have plenty that are not equivariant, and just one that has the property that we like, multiset-equivariance without set-equivariance. So what is this DSPN thing? It stands for Deep Set Prediction Networks, which is a paper from NeurIPS 2019. The details of why this works aren't so important, but just very quickly, the basic idea is that we first relate a multiset Y to an input vector Z through loss and latent space, like this one here. Then we try to find a multiset that minimizes this loss by gradient descent, and the best multiset we find is our prediction. So, in the forwards pass, we do this optimization of the multiset conditioned on the input, and in the backwards pass, we differentiate through each step of the optimization. It's okay if that didn't make much sense. The important part is that there's something particular about these gradient descent steps. In the set encoder that gets differentiated, numerical sorting can be used. Its gradient is used to update the multiset, and you can prove that this gradient of the sorting is not set-equivariant, but it is multiset-equivariant, exactly the property that we wanted. And to me, this is really cool, because in the DSPN paper, they found that having a sorting in there was much better than alternative like sum or mean pooling, but they didn't have a great explanation as for why this is the case. Now we know. With the sum and mean pooling, you get set-equivariant gradients, but with sorting, these gradients are multiset-equivariant and not set-equivariant. So, by using sorting in the encoder, DSPN is able to separate equal elements. Despite this, it turns out that one of the state-of-the-art models, slot attention, works remarkably well and is often actually better than DSPN, even though slot attention is set-equivariant. So, let's see what else about DSPN we can improve. One of the main mechanisms in DSPN is this optimization, and normally we just use automatic differentiation to backpropagate through the optimization steps. There's actually a much better way to do that with implicit differentiation. Implicit differentiation tells us that instead of having to differentiate every optimization step, we can get away with only differentiating the last step and solving a tiny linear system. Doing this has a lot of benefits. Differentiating one step obviously uses less computation than differentiating many steps. and we also save a huge amount of memory. We now only care about what happens in that last step, so we also only need to keep that one last step in memory, rather than the whole thing. So, in an implicit DSPN, we still use automatic differentiation for most things, but we switch to implicit differentiation when backpropagating through the optimization procedure. This lets us use more optimization steps in a better optimizer, both of which should lead to better results, for the same model size, same total computation, and less memory. We can even skip solving the linear system that is normally required for implicit differentiation, making it faster to run and easier to implement without any loss in performance. How well does this actually work in practice? It turns out extremely well. There's this clever object dataset where we have these images of 3D scenes as input, and we want to predict the set of objects and all their attributes. For example, this object here we would want to be predicted as a large purple metal cylinder at these 3D coordinates. For an element in the prediction to be considered correct, every attribute has to be correct and the 3D coordinates have to be within some distance threshold. If we set this threshold to be pretty strict, the regular DSPN gets 1% average precision, and the previous state of the art, the Set-equivariance slot attention, gets 8%. After adding implicit differentiation to DSPN, the set-equivariant version with some pooling gets 49%, and making it not set-equivariant but multiset-equivariant by using sorting, it gets up to 77%. That's massively better than any existing result. And best of all, we don't need to train nearly as much to get there. On similar hardware, we only need about 6% the number of effective epochs and training time of slot attention. At least to me, it seems like for set prediction, the inductive bias with multiset-equivariance is much better than with set-equivariance. And that kind of makes sense, since set predictors operate on lists that represent multisets, not sets. So, to summarize. We started with seeing that set prediction models operate on multisets, but they are usually set-equivariant, including the popular slot attention and transformers. This is too restrictive. They can't separate equal elements or have difficulty separating similar elements. So we came up with this new notion of multiset-equivariance, which doesn't have this limitation. We found that DSPN with a specific encoder using sorting is multiset-equivariant and not set-equivariant. Lastly, we saw how we can use implicit differentiation to make it faster and more memory efficient. This lets us improve the state of the art by a huge amount. Of course, this isn't a be-all end-all solution to set prediction. One major problem so far is that it's a bit difficult to make it work well on a real large-scale dataset, so there's definitely plenty of room for improvement. And it would be nice to get a better theoretical understanding of multiset-equivariance, for example, what ingredients are needed for universal approximation. In general, these kinds of symmetries are everywhere, and identifying the right structures, like we did here with multiset-equivariance for multisets, can really help a model be much more performant and data efficient. If you're curious about the details of this work, have a look at the description with a paper, open source code, and pre-trained models available. This has been worked by me and David Zhang as eco-contribution first authors, a collaboration between people of Samsung SAID AI Lab Montreal, University of Amsterdam, Mila, University of Montreal, and TNO.